And when I put the solutions in Canvas, it's at the end of module 3 though. So go all the way into module 3, you'll see the solutions. There's a blank copy there too, if you want a blank copy. Hey, today, this is the fun part, at the end of the course, the last module, we just go backwards. We do antiderivatives. Now, it starts in 4.9. So today we start in 4.9 and we'll get up into 5.1, where we build off this concept of antiderivative. It means just go from velocity back to position. Go from acceleration back to velocity. And so we just need a reverse power rule. That's what we need. We need a reverse power rule, like something like this. X cubed would go to 3x squared. We need to somehow come up with an expression of how you go from 3x squared up to x cubed for this antiderivative process. You could probably figure it out on your own. This power has to get added by how much?
1.
1. So that's part of it. So the rule will be, all right, let's add 1.
Don't you have to account for a constant too?
Good call. There you go. We have to account for any constant that might pop up. And when he's pointing out like the x cubed plus like 5 or something, and the derivative of a constant's always what?
3.
0. So we'll have to figure out like what to write every time because there could be a constant there or something.
Did you multiply by the reciprocal to get rid of the 3?
And that's what we'll do. That's the rule. So the rule is, I guess we'll just say, take this expression you got, add 1 to the top, and then divide by that number. Just like that. That'll be the antiderivative expression. And then Ben says, but wait, there could be a constant in the original thing, so every time just put a plus C on it. A plus constant. Just every time put a plus C. Well, let's try one. 3x squared. Pretend that was the derivative of some function. Can you figure this out?
Yeah, so x cubed.
And hey everyone, I'm writing it this way. I won't write it like this forever, but it's the idea of, oh, we're going backwards, so I'm kind of writing it backwards. We got to go from 3x squared and back to the original f of x. So the rule is, just add 1 to that power. What about this constant here? Just include it. Remember the constant rules, we just keep constants in front?
Mhm.
Cool. So x squared would become x to the
3rd.
3rd?
Mhm.
But then now you gotta divide by the number you just wrote. Maybe I should put that in yellow. This is the first time we're doing that. I'll get that out of the way. We added 1 to that, right? But the rule says also you gotta divide by that. Whatever that power was right there, you also gotta divide by it. So x cubed over a what? 3. And then I'll always write plus constant. Ben says there could be a constant there, so we'll take care of that, no problem. How about every time we write plus C? Unless you want to write plus K. It's C for constant, right? Or think of a person's name like Charlie. Plus Charlie. Every time, just plus Charlie. And what happened to these trees? They cancel. So is that right? That one is the derivative of x cubed 3x squared? Does that make sense?
Mhm.
So we're doing antiderivatives. This is 4.9. We'll spend a lot of time in here. Make sure you're pretty good with all of them. What about trig functions? Well, no problem here. We'll just go that way now, right?
Mhm.
What's the antiderivative of cosine of x?
Sine.
Sine of x. What's the antiderivative of sine of x? Negative cosine of x. What's the antiderivative of negative cosine of x? Negative sine of x. But we should put those other trig functions down. What was the derivative of tangent of x?
Secant square x.
So how about, I'll just write this below it. And I'll just put an arrow like this indicating differentiate. I'll put an arrow like this to mean antiderivative. So the antiderivative of secant squared of x is
Tangent.
tangent of x, and then I'll put plus c, right Ben? I'd have to put a plus c. We don't have to write that over here. We'll know, always put plus c. There could have been a constant there because the derivative of the constant would be 0, we wouldn't see it. We'll just plus c everything. Do you remember secant's derivative?
Secant x tan x.
Secant x tan x. Alright, I'll put an arrow for differentiate. So we're good, there's the traits. Wait, aren't there two other trig functions? Yeah, they don't come as often. If you wanna put them down, you can, you just put an arrow up, go up that way. If you recall, like, I can speak about them. Cotangent x, the derivative is negative cosecant squared. So negative cosecant squared and cotangent x would do the same. Want me to write those?
Yeah.
I'll put them down since we haven't seen them in a while. Have you noticed they don't come up often? I know, you're like, you rarely see them, I'll put them down. Cotangent x, its derivative was negative cosecant squared x. Well, then the antiderivative of a negative cosecant squared would be a positive cotangent x. And then the other one was cosecant x, which was negative cosecant x, cotangent x. And then, just see, I'll pick problems from the textbook, see how often these come up. Not too often. Alright, let's try one. How about, the first few times I'm gonna write it this way, because I'm trying to emphasize it. We're just going in reverse now. Like this is velocity, this would be position, right? If this was acceleration, this would be velocity. So how about x to the fifth minus 4x to the third plus 2x squared, yeah, I'll leave 2x squared, plus 5x plus 7. Alright, we gotta do all 1, 2, 3, 4, we gotta do all 5 of these. And we're gonna find the antiderivative. This is called a polynomial. Well, each one of these are these monomials. We'll do each monomial separately. What would x to the fifth become?
X to 6 minus
Good job. Look, he pumps it up by 1. He pumps the power up by 1. And then he just divides by that number. That's what this rule means, right here. Pump up that power by 1, then divide by it. Alright, then there's a minus. Cool. Good, Jess?
So you only have to do the plus C at the end, right?
That's right. You don't have to put 6
For
plus
each
C's.
one. Okay.
But, because think about it, I wanna point this out. You wouldn't be wrong if you put 6 different variables down. But 6 unknown constants that we don't know is just one unknown constant. There you go.
Okay.
I'd be like, I can't mark Jess wrong. She put plus C plus D plus E plus F plus G. She's saying these are some unknown constants, but they could sum to 1 plus C. Alright, that 4 stays. What's that become?
X to the power 4 divided by 4.
Now do you wanna do something? Make it look pretty?
Yeah.
Yeah, let's do it. Alright, the 2 stays. X squared.
2,
Three.
3, 6.
3.
X, you pump it up by 1, x cubed, then you divide by that number. Hey, how could you check these?
Take the derivative.
Yeah, I want just every time you like, I don't know if I did it right, just differentiate it real quick, you should pop right back to where you were. Take the derivative. Okay, 5, x to the
2.
over.
2.
Alright, be careful of this.
7x.
I don't know why, you got it. Some people put 0, because we're so used to derivative of constant 0, so they're thinking derivative, but the antiderivative of 7, you're saying is just 7 with the letter
X.
x to a 1 over 1. Well, 7 is. And now finally, I'll put down the plus C. Plus constant. There it is. Now, somebody got it? Oh, what's that?
Would 7x be over half something?
Yeah, but you don't have to write it. You know why?
Oh, it's fine.
Good deal. And you figure it, you're like, oh, it's 1. It'd be over 1. You're like, I don't have to write that. Just remember, constants turn into that number with the x. And maybe there's a constant here, because the derivative, like, maybe there was a 17. We're trying to figure out what it was. the original thing. Maybe there was a 17 here, and the derivative of 17 was 0. That's why we just write that every time. Antiderivatives. Alright, so if we know all the tricks, we got every type of like polynomial down. Let's look at the strange cases. You go, what are you talking about? Like square root of x. Let's look at that. You know, sometimes things are to the 1/2 power. Well, let's start slow and then build off that. By the way, you don't have to write it like this in your notes. Section 4.9, every time I teach calc, I'll spend at least the first portion of class going up this way, just to emphasize, oh, we're going in reverse, right? But in your notes, you might write this underneath this, that's nothing wrong with that. We gotta make that a power, x to the what?
Half.
Alright, now you gotta pump that 1/2 up by 1. I don't know how great you are with fractions.
3s.
Good job. I mean, seriously. If not, you'll probably get used to it. If you're ever like, I can't stand fractions, you pull out that calculator and go, what's 1/2 plus 1? You know, and fract the thing. But yeah, 1/2 plus 1, you got it, 3/2. So I'm gonna get x to a 3/2. Now I have to divide 3/2. Now that looks kind of sloppy, doesn't it? So when I think about this in math, you'll get used to this as well, because you'll do it like 100 times. No lie, 100 times. In math, if you divide 3/2, that's the same thing as multiplying
2/3.
2/3. So I'm just gonna take my chalk here and just flip it, right? 2 here, 3 here. Did anyone say that? It means the same thing. It looks better. That was really a complex fraction the way I was leaving it. We shouldn't leave complex fractions, so we shouldn't write it as x to the 3/2 over 3/2 or over a 1.5. We should write, flip it, 2/3. Oh, and don't forget my plus what?
C.
Plus C. Will the plus C ever become really important? Yeah, a couple problems. And they call them initial value problems. Initial value problem will be a problem where they give you an initial value and it gives you enough information to find C. So I'd like to give you an example of that. So and every time we're just gonna put plus C, right? But what if there's an initial value problem? You go, what does that mean? It means they've given you one initial value from the function. Alright? Right? Stay right there. This is given. This was given to you in the problem. And the question is, find the antiderivative of this expression. So we're going to go find f of x again. I'm going to write down exactly what we had. But this is going to allow me to figure out the constant. Okay? That's what it's going to do. So they call it an initial value problem, or they call it that. Who's going to take differential equations eventually? That's what they, IVP. You'll see this little IVP, initial value problem. See calc did. So all right, they just means they gave me some initial value from this function. Well, I'll do it again. Here's f of x. X to the 3/2 divide 3/2. Wait a minute. That looks weird. I say multiply what?
2/3 plus C.
2/3, so it looks better. Right? And then I never forget to write what?
C.
Plus C. Now we wrote that. We're going to dive in here, substitute things, and we're going to figure out the constant. Okay. So I can erase this part here, get this out of the way, so we have room. I'm done except for one thing. All this is right, I want to figure that number out. This allows me to find C. So when they write this like this in math, you don't want to freak out. This is the letter X, this is the letter Y. So that's X, that's f of X. That's X, that's f of X. That's X, that's Y. So put in X right there. It's 4. We have equals, there's 3, put the 3 where? Here. And then You get 2/3 of 4 to 3 halves equals 3. Now, Ron, if you're like, I don't know how to do 4 to 3 halves, I know the calculator does it, but you don't need a calculator. It means the square root of 4 cubed. That's what that expression means. It means the square root of 4 raised to the third power. Now, I know you can do that in your head.
8,
But square root of 4 is 2.
8.
So when they do those, they do numbers you could do in your head. But if you have to, pull out the tool, figure out what that is. We're gonna get this C eventually. Right, that's 3. 2/3, Art, thank you, you said this is 8. When you multiply fractions, just glue across, right? 2 times 8